then we come to the next talk, and I'm going to present on SpeedyWeather.jl, which is a model that I've been working on for, let's say, like the last year or so. There's a couple of, actually quite a lot of contributors that have contributed different amounts in different ways. Some of them conceptually, some of them have written entire schemes for it. And SpeedyWeather.jl has a slightly different approach in the sense that it is not supposed to be like, I do not necessarily see it as like really being like a full-blown atmospheric model, but it's more, I always see it as like a computational research playground. So really more on the side of like being a little bit simpler and therefore not necessarily always being like, I don't know, highly tuned in order to represent certain climate or atmospheric processes very well, but really basically being just like a playground of like, how can we actually create something like a relatively easy usable climate model in Julia that is also customizable and composable, which Greg already talked about, and you will definitely, yeah, there's definitely a lot of inspiration from Oceananigans that went into SpeedyWeather.jl. But my initial motivation for this was when I probably saw pictures like these ones, which I think is from a tweet from AGU at some point, where someone built a hurricane in Lego. And I feel like every time I try to explain people what Speedy Weather is supposed to be like, I somehow use the word Lego in it, because I feel like I want to be able to have a model where you can literally, as easy as in Lego, you can kind of just like take out certain parts and put in new parts, right? So if you ask a 5-year-old here now, like what would a hurricane look like without precipitation, they would probably just take away the blue pieces. And this is exactly how easy I want a climate model, or like an atmospheric model in this case, to be, so that in the end, the only thing you really have to define are the interfaces, right? So like the little nibbles that stick out in the other parts of the Lego pieces in order to like get them together. But you can actually, if you wanted to, you could replace the blue Lego pieces with like purple Lego pieces representing, I don't know, ice instead of water, for example, right? And so at the moment, SpeedyWeather.jl is at a stage where you can like play that video, is at a stage where you can run the primitive dry core and wet core on the globe. It uses spherical harmonics to discretize the equations of motions. And so we're in contrast to many of the other models that we've heard, or like especially Oceananigans, we cannot run just a specific region. We always have to use the entire globe because of the spherical harmonics. But also there's definitely a focus at the moment on the atmosphere. For example, here you can see that there's not really an imprint of the ocean on your surface temperatures. So these are surface temperatures. You can see mountains, yeah, but you can't see the ocean. This is simply because the heat fluxes with the ocean are just not implemented at the moment. And so this is where, yeah, basically we have kind of filled up the entire ocean with concrete or something like this. And so in order to kind of like present a little bit, I'm going to do some live coding. How that, I'll make it a bit bigger. How you use Speedy Weather it's very, very similar. I kind of definitely took a lot of inspiration there from Oceananigan, where you like once you load the package, let's execute that. Every live of a Speedy Weather simulation always starts with a spectral grid object. The spectral grid object is kind of like the grid object in Oceananigans, and because it's a spectral model, you have to define the resolution in spectral space. So this is the resolution that is often called T31. So it means it has about like 400 kilometer resolution, so pretty fairly coarse-grained. But you can specify the different grids, and we will talk a little bit more about grids at the end. For example, here now we use 6 vertical levels. You just basically define the Earth with a default radius, and for example here we use this octa-helix grid that I will specify later. But basically, the first thing you always do is you define the kind of like the physical domain, which is hard-coded. It has to be a sphere. But then the discretization is the first thing, the first object you always define. And then in a similar way, you start building up all your components. So let's say one of the components you want to have, you somehow want to change the orography. The next thing you would do is that you define an orography object. And so for example, here you say like, I want to use Earth orography. There's technically even like you can specify like the file that's going to read from and so on and so forth. But in the end, you just have like an object that represents your orography. And you do similar things, for example, for also the let's say, I mean, these are more like the physical parameters of your simulation, but also for like the numerical things like horizontal diffusion or some of the physical parameterizations, let's say like large-scale condensation, where you say like, you always create these like, this is the typical scheme that is in the Fortran version, which are kind of used as like a starting point to build this model. The very simple condensation scheme in there then basically can be changed by just passing on some parameters. But in the end, you really start building up the model from individual building blocks, and then you construct a model. So you definitely see some similarities there to Oceananigans. Here we call this a primitive wet model. So it's the primitive equation model with humidity. So that's why it's wet. Yeah, you pass on the grid. You pass on all the components that you do not want to have as the default. And so you get this model object in the end. The model object is then, because basically, in general, you often end up in the situation where like these different components of your model still have to talk to each other before you actually start the simulation. Meaning, for example, if you're on a planet that defines a certain gravity, but some of your schemes need to use that gravity component in order to pre-calculate some terms. This is basically what's going to happen then in the next step, which is this initialization step. So initialize the model, then you will get a simulation object back, and then you can run the simulation. And I think now I can also just do this. That should work. Up. And then basically just run through, and it continued from the previous 5 days. That's why the plot looks a bit different now. And we just use the Unicode plots here to give you a quick peek on the surface relative vorticity. You kind of see that, okay, there's some mountains, there's some like low and high pressure systems that are in the mid latitudes on both hemispheres. And so this is kind of like the this interface that we use in order to play around with Speedy Weather, and I've found this absolutely useful to kind of really think in terms of these like building blocks, putting the things together, constructing the model, go to the simulation, and then run the simulation. And that also makes it really easy then suddenly which you cannot really do in a Fortran model, right? Where you're like you can only play in the Fortran model in the same way as in the way that the developer wants you to. But here you basically just have this object simulation, and you could just look afterwards at, let's say, the diagnostic variables of then the surface, and then you look at the large scale precipitation in there. And if you plot that one, it would be just directly, even though we are on a very funky grid, this octa-helpix grid, and still you can just like look at, this is just the accumulated rainfall due to large scale, so that just happens in the mid-latitudes, hence you see some signal there. And you can basically, exactly in the same way as like Greg defined Oceananigans as a library, you can also basically use this here as a library, because you suddenly can interact with the simulation object in itself, look at the individual things. You can use the components of the model individually, so you can define different grids. In the end, this is just a grid which basically just has values defined on various grid points. And the model then knows it's an octa-helpix grid, so it has to do some interpolation in order to display it for you as in terms of a matrix, because it has reduced numbers of grid points towards the poles. And you can, for example, still then use, like, let's say, the interpolate function from Speedy Weather, which we have in a sub-module that's called ring grids. But basically, because suddenly everything is like agnostic of the type of grid that we have, we can just like reuse these operators. And we feel like this is really like going us into the direction where, yes, you have a model that has certain operators that run something, but as a user, you can use exactly the same operators again, instead of just running a Fortran model, and then you have to think about, oh, how do I actually calculate a curl on this funky grid? No, this would obviously then do this for you. Exactly. I'll just jump back. So what I absolutely wanted to avoid with this, what what I absolutely wanted to avoid with this way of constructing a simulation and building this like model from the bottom up is that many of these like more traditional models have these monolithic interface. So meaning as a user, you somewhere sit at the top, you can change what the developer wants you to change, meaning some kind of name list or config file. And then once you then hit play, the model will start usually like by constructing some kind of primary components and then some secondary components, and then will somehow run a simulation. But your interface to the model is really here at the top. Meaning that if you ever want to change the green block, which might be some scheme, so let's say, I don't know, precipitation or so, and you want to have a different precipitation scheme, you usually, as someone who wants to like hack around with the model, you somehow have to know what the interfaces between the green, the blue, and the yellow building block are, and you somehow have to like branch off, create copies of that, and somehow make sure that whatever parameters you throw in at the top somehow make their way actually down. And if you have this other philosophy where you kind of like, where you start building the model from the bottom, you do not end up with this problem because you basically just define a new type here in green that basically then runs upward. And so we kind of realized that this is kind of the information flow diagram for SpeedyWeather.jl. So as a user, the first thing you always do is you create a spectral grid object. Based on that, you then you can define all your components as you like. You can define a new planet. You can define a new atmosphere. The atmosphere usually just has like the different like gas constants, for example, in it. But you can also define individual components like radiation, precipitation. You can define different numerics as you want, and you kind of just basically, they all need to basically have passed on then the spectral grid, but otherwise you can construct them independently. And then you put them all into a model object, right? I've shown you the primitive wet equation, but you can also do this with like the shallow water equations or the barotropic equations. And you kind of then have this model object, which you then can initialize. Doing this initialization step, it creates the simulation object, which is split into the prognostic and the diagnostic variables. And then what we really try to do is that the information always resides in the prognostic variables. It then passes that on, because this is in spectral space, passes that on into doing a spectral transform into the diagnostic variables, which most of them sit in grid point space. You may use some of these like pre-computed stuff of the model. So that could, for example, be things like some terms that you already had to pre-compute. And this is kind of like how then one time step is passed on from like going on from like the first time step to the second to the third and so on and so forth. And I found this really useful to write this kind of information flow diagram, because it really shows you like this, like which should depend on what and not on which other components. Yeah, there are definitely ways where you have to somehow find kind of like ways to kind of like tweak that. So there's a lot of schemes, let's say these adaptive schemes, which for example change once the change, like the change with the current state of your atmosphere. Those ones are obviously tricky because technically they're then diagnostic variables and they're not model, because suddenly you would have an information flow going from the diagnostic variables to, let's say, the model component that describes this adaptive scheme. So that's always a very, very tricky one, but it's very good still to know exactly when are you breaking with this concept. And so I think, yeah, as the next point, and as the last point, I just want to show you how you can conceptually extend this model. And I think this is actually fairly similar to how you would also do it in Oceananigans. So let's say, for example, we have this abstract supertype abstract condensation. So this is just like the kind of scheme that does the large-scale condensation inside the model. And you could now define a new one by just subtyping that. You may need a couple of parameters. You can define them in here. You have, for example, some pre-computed arrays. That could be just vectors. That could be, you can just initialize them with zeros. But what I find very interesting is that you can also think of this as, and this is kind of where we go back to what Chris Rakaukas was talking this morning about, where you actually can think about this as just some data that sits within the scheme that you want to use. So it could be also a neural network. You may just initialize it with zeros or whatever. But then the second step that basically every component in SpeedyWeather has is this like initialize function. So initialize then you pass on you define this for your new type microcondensation, and that, for example, can then either read in the pre-trained values for your neural network, or you, for example, does some computation so that you actually then end up with, like, for example, you want to calculate a term like, I don't know, gravity times whatever else, and you kind of don't want to do this on every time step. And then the third component that every scheme needs to have is then the actual what it is supposed to do, right? So like the model object has a construction, an initialization, and a simulation phase. The condensation scheme has a construction, an initialize, and like the actual like condensation function then, for example. And then you basically actually tell it what it's supposed to do. And like in this simple example, you may say like, okay, my condensation wants to be, if my relative humidity is higher than 100%, then do something to the tendency of your humidity. So this, for example, would then go here where the 3 dots are. And what I find quite interesting about this concept is that once you say using SpeedyWeather, you have this like abstract condensation supertype available, and you can define this entire thing completely outside of the model. And then basically you do go through the same thing, but then you just define a new large-scale condensation object that's just then basically calling what you've just defined, and you can just pass that on as you did before. So it's really like an extensibility that is, you can literally just do this in a Jupyter notebook, as I do here. Maybe I should have used Pluto, but this is just in this Jupyter notebook, and you can see that this is kind of like, I feel like this is a nice way, and I feel it's very similar also to Oceananigans does it, a nice way to basically have a model that is hackable, that really remains hackable. We're definitely on the performance side, not quite there yet, but I feel like we have some answers of this idea of like, how do you create a customizable model? And this is where I would like to end. Thank you. Simon, question.
So I guess the question is, maybe it's a bit of a build-by question. How do you decide what? I guess the question is, how do you decide what should be extensible and what shouldn't be?
That is a very hard question, and I've debated that a lot of times, because there's a few things that where making something, or like, I call it always like abstracting it out. So you say like, for example, you start writing your model and then you start writing your, let's say, time stepping scheme. And the first thing you do is you just hard code everything. You just like, okay, I want my time stepping scheme to be this. And you just hard code it. And you could then think like, okay, maybe I want to have this flexible in the future, and you kind of make it abstract. And I feel this is something where it absolutely depends on the use case of your model. Ideally, you would like to abstract them all out. But it's also a question of, it's a lot of work, right? It's a lot of work to actually do this. And so for this model, for example, I've decided to focus on these like physical parameterizations. So for example, condensation and so on, to kind of have them separate, because they have a relatively easy interface in the sense they're all called at the beginning of every time step. And so swapping out one for the other is a much easier task to do than, for example, being able to say like, my time stepping should be, I don't know, leapfrog, or I want to have like a Runge-Kutta scheme and so on. Because suddenly if you change out, let's say, the time stepping, there's like an entire chain of things that you actually need to make flexible. And so there's a few things that, you don't want to make flexible, but other parts that are relatively easy to make flexible. And so, there's always a trade-off, I think. There's always a trade-off, but I feel, Julia, this trade-off is like far beyond where it is with many of the other languages. Yeah.
Okay.
Other questions?
Just a comment that question is all over the place with we have talks where people are writing general PDE, trying to write codes for general PDEs, and in that case they're abstracting the dynamics away. Here, we are doing you've got a fixed global spherical coordinate system and some flexibility on the dynamics. So I'm just saying this is a big question. I go back and forth between different talks here, and people are taking very different approaches to this question of what's generalizable and what's not. And I'm interested in what do you think, for example, of SciML's attempt to, or Daedalus, to build a general PDE solver?
I find Daedalus is a really nice example because, they have tons of showcases where it's very clear that it is a software package that is supposed to be used in many different fields, right? They have all these astronomy applications as well as general fluid dynamics and so on and so forth. So it's really, that is really the aim of Daedalus, right? So with Daedalus, you want to be able to just quickly write in your own equations. I feel with an ocean or an atmosphere model, you do live within certain constraints, right? You may say okay, I want to solve some weird other differential equations on the sphere. Fair enough. But I also feel it is not necessarily the job of an atmosphere and ocean model to always allow you all of the flexibility. In the same way you mentioned this idea of differential equations where you probably have I don't know how many 20 different time steppers in there implemented, and you can just choose one. Once the models get a bit more complicated, it's not necessarily worth the effort because many of them may not be as stable if you combine them with other schemes and so on and so forth. So there is always a trade-off, and I feel we have to be aware of where the trade-off should be, but everything else I feel with Julia, we can absolutely make everything else very flexible. Yes, Skylar.
You described it as a computational research playground. I'd love to know, where would you like to see your user community grow? Where do you think, what would be your dream for who would use it?
Yeah, that's a good question, because I feel in the last years I've always written models basically more for myself. And I've never really had this, let's say large team. We have one goal. We want to create this model in order to actually create a big user base. It is tricky. It is definitely tricky. What I would absolutely love to do personally myself, and I would love to see other people doing it, is if you, this idea of Speedy is basically that you have a dynamical core, and you have a bunch of different parameterizations, let's say condensation, radiation, you have all the ocean heat fluxes and so on. And I would absolutely love people to see, to just implement their own versions of it. So for example, just playing around with what's going to happen if you if you increase the rainfall here a little bit, right? What does actually then happen? Or can you replace a few of these components with neural networks? Can you replace all of them with neural networks? Making the entire model differentiable is another thing that I would absolutely love to see, but it is definitely looks like a very hard topic, not as easy to be done as said. But maybe with Julia, we're actually getting into that direction, right? We're going to have another talk later on differentiable models. But I feel at the moment, I would love to see people playing around with the physical parameterizations. I think that's the best place to currently play around with it. Yes. I want to pass on the microphone.
Oh, sorry.
I'm familiar with some of the more mature weather forecasting tools like weather research forecasting.
Yeah.
Can you compare this to weather research and forecasting in terms of intended purpose and how far along it is in terms of matching WRF's capabilities?
I've never used WRF myself. But it's also very much supposed to be used as a regional model, right? To really do these kind of things. No, I think this is also just the human capacity at the moment. This is I think 90% me writing this model, and so I feel it's impossible to leverage that. So you have to sometimes with some of these models, depending on how much human resources you have behind it, you have to aim for a certain niche. And I feel here the niche is really to design a more conceptual model that does something different than its a Fortran counterpart, and really to show how these things can be done differently. I would love to see it as yeah, it's something that we can also just use, for example, in teaching, where you can simply say, I mean, this is similar to Oceananigans, right? You can literally like set up a simulation in a few lines of code, have it like swap out different things, and you could actually now just say like condensation equals false, and like kind of, I mean, hurricane is probably a bit small for the resolutions that you can create here, but otherwise you could just take out the precipitation in a hurricane and see like what actually is different then suddenly, right? Yeah. Rough. And then we should go.
If Julia really wants, as a community, play an important role in climate science in general, it seems to me that the way to go would be to have one very performant dynamical core, because we are always solving the Navier-Stokes equation, ocean and atmosphere. Then the modular part, you want the parameterization, because that's where the scientific advance is actually happening. But in a sense, what I see is a proliferation of dynamical cores in some sense that, I mean, it is useful, but then it becomes niches, sub-communities, and it's hard to see how this kind of exercise will really play against the large community models that are being run by centers around the country.
Yeah, no, absolutely, I agree. Like when it comes to the big, to these like really large models with like big development teams behind it, I absolutely agree on that. That we know that the highest uncertainty comes from representing any kind of climate processes, whether it's in the ocean or in the atmosphere. And so in order to kind of to create a model ensemble that runs a climate prediction into the future and gives you like reliable uncertainties, you do want to max out the model ensemble exactly where the uncertainty comes from, meaning like all these climate processes are not necessarily the dynamic core. So technically, we should all stop what we're doing and just develop one dynamic core. I agree with that. But I feel also we still have to produce some kind of these like prototypes in order to kind of like remind people of like, hey, actually, if you start from scratch, we can do things differently. And I feel like a lot of the, let's say, especially like the models that are currently used operationally, right? So you mentioned numerical weather prediction. Those are sometimes a little bit stuck in their own world. And I feel like coming from Julia, we definitely have the chance to reinvent things from scratch. And I feel this is very like, and I hope this kind of like, not triples downward, but triples upward to the big operational models. Okay, I think we should go to the next talk.